The period of an oscillating function is the time required for the function to complete its full cycle. To find the period, one can simply measure the time between when the function is in a given phase and the next time it comes back to that same phase. So in this diagram here, at this point, the function is in a certain phase, and then when it comes back to that same position, it's in the same phase again. So we just want to measure the time between those two occurrences, and that's the period capital T. If you know the frequency of your function, then you could find t by dividing 1 by f. And the frequency of the oscillating function is the number of cycles or repetitions that occur per time. So it has formulas of f equals cycles per time, or f equals 1 over t, because frequency and period are inversely related. Frequency has the units hertz, which is written as capital Hz, and it is cycles per second. The angular speed of a periodic function is the fraction of a cycle that is completed per unit of time, and there are formulas for it that we'll use in this example below. One way to find the angular speed is to divide 2 pi radians by the period. The angular speed gets multiplied by the variable t in the argument of a trigonometric function such as sine or cosine. Omega is the variable that stands for angular speed. Now, if we were to change the angular speed of a function, that would be like performing a horizontal stretch or horizontal compression of the function. Like a spring or slinky, we could smash it closely together, or we could stretch it way out. Find the angular speed of the graph. So we can use any of the formulas above. I'm going to use the formula omega equals 2 pi over period because I think that'll be the easiest approach. All we have to do is just measure the period of this wave, and we can do it because the horizontal axis here is time. So in order to measure the period, we just have to find when the function's in one phase and it comes back to that same phase. And let's just get the time between those two events. It looks like 3 pi over 2 seconds. So we'll do 2 pi over 3 pi over 2 seconds. That's going to give us 4 over 3, and then our units of angular speed will actually be radians per second. Now, what would happen to this graph if the angular speed were to be increased or decreased? To investigate this, I'll go to desmos.com and we'll just plot a periodic function. Alright, so here I have the graph of y equals cosine of 4/3 t. What we want to do next is change the angular speed. The angular speed is the 4/3. Now, if we double it to, say, 8/3, what will happen? Will it be a compression or a stretch? Well, it is a compression. And if we were to go to 16/3, that would mean more radians per second. Then it's a compression yet again. What if we were to go the opposite way? Instead of 4/3, I'll make it 2/3. Now it's a horizontal stretch. Yeah, so the angular speed does control how our function looks and how quickly it repeats in time. So when omega increases, there is a horizontal compression.